Hello, good afternoon, everyone. So today's we are seventh week of the l- online live session for the problem solving. So earlier classes we are talking about the molecule, not talking about that any reaction. So today's classes we mainly going to solve some problems related to that some reactions, and this reaction are SN1 type of reaction, that is the substitution reaction. So before start, so first I am introduce myself. So me Povir Maithi. I am PMR student from Aijar Mohali, and that course name is Symmetry, Stereochemistry and Application, and course instructor Professor Angsuman Roy Chaudhary. So what is SN1 reaction? The SN1 is the substitution nucleophilic unimolecular. Unimolecular reaction means that at the rate determining step only the concentration of that your substrates only involved, not your living group. But for the SN2 reactions, the rate determining step that both the concentration of substrate and living group both are involved. So reaction is a type of nucleophilic substitution reactions in organic chemistry. It involves substitutions for a living groups in a molecules by a nucleophile. The reactions proceed through a two-step mechanism. So one step is the formation of carbocation intermediate, and next step is that the living attack, nucleophile attack. Sorry, nucleophile attack. So first step is the ionization or the formation of carbocation, which is the rate determining step of this SN1 reactions. So for SN1 reactions, if they are from carbocation, and you know that carbocation will be stabilized in polar protic solvent, because the polar protic solvent chances of that hydration of polar solvent will be high, and that will stabilize this your carbocation or also the living group. If your solvent is non-polar, then SN1 not that much favor, because that time your living group are not stabilized by their solvent. So SN1 is favorable in that polar protic solvents such as water and alcohol is often used at the SN1 reactions, and the polar solvent helps in the dissociation of the substrate molecules into ions. So polar solvents helps two-way. First is the dissociation, because there will be some electronegative group attached into this uh, alkyl carbons, and when this electronegative group, so it will be del plus and del minus, and your polar solvent make to separately dissociate both that states, and which we can get that carbocation easily. If there will be non-polar solvents, that's not possible that these two, one is the alkyl and one is halide, are independent stabilized into the solvent. So there will be very much role of the solvent into the SN1 reactions. where that the polar solvent can dissociate your substrate. The leaving group X departs from the substrate and leaving group leaving behind the carbocation a positively charged carbon atom. This step is often the rate determining step of this SN1 reaction. Then next step is the nucleophile attack. The carbocation formed is highly reactive and can be attacked by the nucleophile. In the solution, the nucleophile attack in the positively charged carbon forming a new bond neutralizing the charge on the carbocation. So there will be carbocation from now your nucleophile will come and these charges are stabilized by the nucleophile negative charge and you are getting a stable product. But sometimes if your nucleophile is a very weak base, so then the third step is needed, and the third step is that deprotonation step. Like your nucleophile which have the hydrogen, so it will attack your substrate, then nucleophile loses its hydrogen because it have sufficient neutralization by this your substrate, so it loses your H plus. So sometimes if your nucleophile is very weak base, so sometimes the third step is needed, that is the deprotonation step. But generally for SN1 reaction, the two-step process, one is the formation of carbocation and next step is the nucleophile attack. Now I am showing that how this SN1 type of reaction is going on. So if you show here, so first your substrate, so this one is your substrate, and substrate have some aromatic that RS nomenclature. So this one your substrate, and substrates, if you want to do that substrates, what is that RS nomenclature, so your this one is your first priority, this one is your second priority, this one is your third, and 1 2 3 it will be clockwise. So clockwise means and your for priority in the above, so clockwise will be S. So this is the S alkyl halide. So first step, so for SN1 reaction what I am telling, the first is that remove of that leaving group. So Br is removed. So now that your carbocation is formed. So now carbocation is formed and your solvent is water. So that in that carbocation, so this will be that empty orbital. So empty orbitals and your carbocation like this way. So empty orbital they have the both side, so it can attack from the front side like right hand side, or it can attack from the left hand side. So after from the carbocations for the SN1 reaction there will be two products can be formed, because this the empty orbitals have the two sides vacant orbital which can get two different product. One is that R and one is that S. So if the path B will follow, so if that nucleophile will attack from this side, so this will be your OH2. So like I am telling, when there will be a very weak nucleophile like water, so then there will be deprotonation step is prompt, so that deprotonation H plus will be removed, so it will be from this product, and which is by RS nomenclature, which is the S. And in the next step, the path A, where the water attack from this left hand side, and you are getting like this product which give as a R. So for that SN1 reactions, we are getting two product from single substrate. We are getting two type of product. One is that R and one is the S. So from S we are getting S. So we are getting the retention, like retention of symmetry. Yes, but this one the pathway process we are getting from S to R product, that is the inversion. So SN1 reaction, the formation of products is two. One is the retain your original original symmetry, and in the next which are not, which are the invert of their your symmetry. Now the key feature of that SN1 reaction, so the reaction rate depends only on the concentration of the substrate, so that is the unimolecular kinetics and unimolecular, that is the unimolecular kinetics, and for this unimolecular kinetics this SN1 one is coming. So the stereochemistry of the reaction is not well defined, leading to the racemic mixture of products and the chiral center are, when the chiral center involved we are getting that racemic mixture product. The stability of the carbocation intermediate plays a crucial role in determining the reaction rate. More stable carbocations leads to faster reaction. So when you give the more stable carbocation, which give the faster reactions, it's important to note that SN1 reactions are favored when the substrate is highly hindered. That is that in the substrate there will be some steric crowding, and how this steric crowding which help to stabilize this that carbocations I will show in later. And the leaving group is good leaving group. Additionally, the nature of solvent can influence the reaction mechanism. As earlier I have told, nature of solvent like polar protic solvent um, which will be give more hydration and which will help to uh, that stabilize your both the both carbocation and leaving group, which helps to give SN1 reaction better. So what are the effect to stabilize this to favor that SN1 reaction? One is the polar protic solvent. So SN1 reactions are often favored the polar protic solvents such as water or alcohol like methanol or ethanol and carboxylic acid. This solvent stabilize the carbocation intermediate through the ion dipole interactions, because this polar protic solvent have that dipole and ion, and which stabilize your both the intermediate and also the leaving group. The polar solvents surrounded to the carbocation and reducing its reactivity. The ion dipole, because in SN1 reaction the carbocation formation is the most obvious states, and if you are not stabilizing your carbocation by anyhow, so you cannot get SN1 reaction because they cannot form that carbocation if it's not stabilized. So the ion dipole interaction also facilitate the dissociation of the leaving group from the substrate. Then the solvent effect on ionization rate. So the rate determining step of the SN1 reactions is that carbocation formation substrate to the carbocation, and the polar protic solvent can stabilize that leaving group through the ion dipole interactions, making easier for the leaving group to depart. So one is the stabilization of carbocation, which helped by the polar protic solvent, and also the departing of that your leaving group. Also that will be easier when we have the polar protic solvent or polar solvent. An influence of the solvent polarity, that is the highly polar solvents enhance the solvation of ions which can stabilize the carbocation. However, extremely polar solvents may also solvate the nucleophile to a significant extent and affecting its ability to attack and affecting the ability to attack the carbohydrates. So it's your solvent is too much polar. So then what will happen? Your nucleophile also the charge species. So your nucleophile will be easily stable. So your nucleophile will be easily can stable by the solvent. So it cannot attack your carbocation. So you have to choose a polar protic solvent, but you have to remember that your solvent must not that much polar that your nucleophile cannot attack and you are not forming the product. So for that you have to remember. So we need a polar solvent, but that solvent polarity not that much high or not that much extent that it can significantly stabilize your nucleophile and which are not available to attack your carbocation. So for that SN1 reactions, I am telling that SN1 reaction is the formation of carbocation is the rate determining step. And how how this SN1 reactions is a first order kinetics follow or second order kinetics. So we can also measure the rate. We can also measure the rate law of these reactions. When we do so, we notice that that rate is only dependent on the concentration of substrate but not on the concentration of nucleophile. So earlier I have told like that SN1 reactions which are dependent on the concentration of substrate, not only the nucleophile. So SN1 is that favor the first order kinetics. Law the rate of the reaction is only sensitive on the concentration of the substance and not the nucleophile. So nucleophile have no role to nucleophile concentration have no role on the rate determining step. So only the formation of carbocations have the role in the rate determining step, and rate doubles when the concentration of alkyl halides is double. So like this is your alkyl halide concentrations, and you increase the alkyl halide concentration. So this is the first, and this is the that is the 1 molar. Like this we consider like 2 molar. So when from 1 molar to 2 molar, so first is the rate is like this in the next cases, and the rate is almost double. So this is the 1, this is the 1x, and this is the 2x. So rate is almost double from first. When we increase the concentration 1 molar to 2 molar, your rate also increase 1x to 2x. So that will so that will tell that only that reactions have depend on that substrate concentration. But if you do that water which is a nucleophile and you increase the concentration of 1x to 2x, so that rate is unchanged on the concentration of the nucleophile is doubled. So when the nucleophile 1x to 2x but the rate is similar, so it's not depend on the concentration of the nucleophile. So it's only so only depend on that substrate concentration, not on the nucleophile concentration. So it's nucleophile zero order in the nucleophile. So it's have no effect uh, on that reaction rate. So only that substrate concentration have role for the Decinon reaction. So for these regions, it's have. So rate only depend on the alkyl halide, that is the substrate. So for this region, so this reaction we are calling SN1. So and also if you that how the SN1 reactivity is follow, like an example when you have the methyl one which is a less reactive as compared to that primary, that is that. So when it is from this one the primary carbocation, this one the secondary carbocation. So as from here to here, so you increase the rate and benzylic due to that when it's the carbocation is from, so which will be stabilized by your resonance. So for these regions the benzylic one is stable and secondary and tertiary. Now the how the carbocation is stable. So a carbocation is general name species the positive charge at the carbon atom. So most carbocations we will encounter are very similar to the neutral boron compounds, like a neutral boron compound which have the empty p orbital. So like a boron compound which have the that empty p orbital and which follows the trigonal geometry and which have the Lewis acid. Why it's Lewis acid? Because Lewis acid and Lewis base depends the who can accept the electron, if there will be your positive charge, and also you have the empty orbital which are very much favored to accept the electrons from the others. So when it will be accept the electron, so then it will be Lewis acid and receive the 6 valence electron and sp2 hybridization. So carbocation have that much that significance that it can behave at the Lewis acid. So for these regions any nucleophile can attack here. So next that how the reaction is going on. So from that, so first step, so when your alkyl halide like Rx and you form that R plus, that is that R plus, which is the transition state, like this way, and you are the X minus, and then you are getting this carbocation like R plus. So when your carbocation stability is very high, like so you have carbocation like 1 degree carbocation and 2 degree carbocation and 3 degree carbocation. So as I am showing, so this one for the 1 degree carbocation, but 2 degree carbocation, the stability of carbocation is more. So now that this will be your 2 degree carbocation. So when it is the 2 degree carbocation, so now that your energy profile diagram will be like this. So this will be your energy profile diagram. So this one, the 2 degree carbocation, sorry, and you getting the product, and product is almost same. So the 2 degree carbocation, so that total energy needed to form the carbocations is less. So for that 1 degree, we have that needed more energy. For 2 degree, we need less energy because your carbocation is more stable. And when the carbocation is more stable, so energy wise it will be less. And for 3 degree carbocation, so carbocation is more stable. So now your energy profile diagram will be like this. So you need less energy. So so you need, so for 3 degree you need more less energy. So from 1 degree, 2 degree to 3 degree, when you are going there, so for 1 degree you need more energy. For 2 degree you need less energy because your carbocation is stable. And 3 degree you need more less energy as compared to 1 degree or 2 degree. So like this way your carbocations getting stabilized. So also why from the reaction coordinate, if you are want to showing that why your 3 degree carbocation is more reactive, because 3 degree carbocation is more stable, so it's less energy. And when we have that less energy needed for a reaction, so when you have less energy needed, so reaction will be fast. And when you have more energy, so you might be give heat, or might the reaction rate will be little slow. You have to give the external energy to give that reaction faster. So why, now the question is why the tertiary is more stable? As the reaction coordinate we are showing that tertiary is more stable from the molecular point of view, like how this tertiary carbocation is stable. So like when you have that carbocation form, so you have the carbocation, like this is your carbocation, and here there will be some methyl group are present. So if there will be methyl group are present, and as you know, when there will be hydrogen which have the del positive charge and your carbon is del negative charge. So when there will be carbocation, so this del negative charge in the carbon atom, adjacent carbon atom, will stabilize this your carbocation. So when there will be multiple carbons present in your in the adjacent to the carbon atom, so then the chance of stabilization of this carbocation is more. So like that way, when we have that electronegative, the carbon is 2.54 as compared to the hydrogen, so that del negative charge will be here. So this is 2.54 as compared to between these two. The electron carbon is more electronegative, so carbon is del negative, and it will be del positive, and this del negative also stabilize this carbon because this have the positive charge. This is a del negative, so it will stabilize. So when you have carbocations and you have the adjacent carbons, and we have that some del positive group attached to that carbon, so that will be more stabilize your carbocation. So for this reason, that when we have the tertiary carbocations, so we have that three carbon, so we have the three carbon adjacent to that your carbocation. But when you have 2 degree carbocation, so you have two carbon atom. And but when you have 1 degree carbocation, like one carbon atom. So for this reason, that that this 3 degree carbocation have much more reactive, or like for a reaction point of view, that 3 degree carbocation is much more reactive. But as a carbocation point of view, the 3 degree carbocation is more stable. Due to this del negative charge of these carbons will stabilize your carbocation. An alkyl group can therefore set the extra electron density to the adjacent carbon and thereby stabilizing it. Therefore, more adjacent alkyl group carbocations are more stable, like this one, the primary carbocation, which have the one carbon atom present, but the tertiary carbocations 1, 2, 3, three carbon atom are present. So the dead negative charge will be stabilized this carbocation, and more donation of electron density, more electron rich and more stable. But for these cases is the less stable. And by the hyperconjugation point of view, how it will be stabilize your carbocation. So the hyperconjugation's explanation for the carbocation stabilization by the alkyl group, it's more satisfying for some cases. Explanation like that carbocation stability is hyperconjugation. That is, that idea is that electrons in the CH bond adjacent to the carbon atom can overlap with the empty p orbital. So when you have the carbocation formed, so their empty p orbital, and the interaction between the bonding orbital of an empty p orbital is stabilizing, and the p orbital of the carbocation as long as they are coplanar, so like they are in the same plane. So in this bond have electron density, and which give this electron density to your carbocation's atom, so that will stabilize your carbocation. But when you have that only hydrogen atom, so this have no bond, so which are not stabilize your carbocation. So we have the larger bond presence near to the carbocation atom, so that will give more hyperconjugation. And when we have the more hyperconjugation, so that will stabilize your carbocation more. Like if you have like this, if you have like this, so the possible hyperconjugation for these cases with increasing. So that your empty p orbital, and it will be like stabilization will happen like such a. So when we think about that pi bond and no bond resonance, like, so now have the double bond, so now this stabilize, so they are making bond. So not an actual resonance from, just a helpful way to thinking that about that interaction. So not that this bond, because that bond have the sharing electron, not that exactly two electron present. So this H plus also cannot be possible. Just to thinking that this positive, if that bond can share its electron to the carbon atom, so this become double bond and which becomes stable. So this predict that CC bond will have the shortened and CH bond will be lengthened. Also predict the pyramidal carbocations will be less stable than the planar carbocations. So the whatever the resonance paper, the observed trends is remains the same. More substituent along the carbocation, the greater is the stability. Now next is that resonance stabilizations. Like when you have the carbocations and you have that adjacent pi group along the carbocations, so that will be resonance stabilized, and your carbocations come, so it will be come here, it will be cos. So overall charges are delocalized, and when we have the overall charges are delocalized, so it will be more stable. So that reduce the overall charge density into the carbocations, making it more stable. In case of each Br's positive charge of 0.5, the resonance hybrid. So concentrate that the carbocations below where the positive charge cannot be delocalized through the resonance due to the absence of neighboring pi bond. So if there will be neighboring pi bond, so that resonance cannot be formed. So this will be less stable, uh, and SN1 reaction is less stable. But when you have that benzene group, so which will be stabilize your carbocation like this way by the resonance, and this will from positive charge here. Then next it will coming here, and the positive charge is giving here. Then the next step is coming here in your positive charge. So your positive charge is going to in that 1 2 3 position, and which will be overall stabilize your carbocation. This pi bond of this benzene group that stabilize your carbocations, and which will help the stabilization of carbocations, and which will be indirectly tell that prepare the SN1 reactions. So now the question is between this question, which one is more stable? So like this one. So there will be three benzyl group are attached to the carbon atom, so that resonance stabilization is more. So it will be more stable than the two benzene group attached, then this one, then this one. No resonance stabilization, only stabilization by the hyperconjugations and your secondary tertiary carbocations. So answer will be this one is that this one is the most stable, this one the second, this one is the third stable, and this one is the less stable. Now between this, which one is resonance stabilized? Like when we're talking about that benzylic carbocation, so benzylic carbocation will be like this. The positive charge is here, so this can resonance stabilize. But when you have the positive charge in the phenyl ring, then there will be no stabilization by resonance. So this one have no stability by resonance. This cases also no stabilization by resonance, but this cases that the your pi that empty p orbital like this, so that will stabilize. There will be no double bond. If there will be double bond like this way, that will stabilize your carbocation. But this due to this electronegative oxygen which have that not share its electron at all, so that are not stabilize your carbocation. So these cases, so no like empty p orbital, and this your hydrogen, and your p orbital will be like this, so no overlap between these two. So no overlap, so no resonance for this cases also, no resonance, that p orbital not coplanar. The next cases one, the D is not stabilized by the resonance because that oxygen, if oxygen give that electron, this will be O positive and only 6 valence electrons are present. That is that by uh, so any orbital have that 8 electrons with the octet will stabilize that orbital, but these are not that octet pillar, so this will be not stabilized. So for this reason that resonance stabilization are not happened. So D is not stabilized by resonance, although the empty p orbital is capable to overlap with the pi bond. The resonance from with that positive charge on oxygen has less than a full octet on a very electronegative oxygen atom, which makes insignificant for the resonance form. Then the next atoms with the lone pair to the adjacent carbon atoms are highly stabilizing, like some lone pair present, like OH have the lone pair to the adjacent to the carbocation, so that electrons can donate here and which stabilize your carbocation. But these cases oxygen still octet because this have the two proton, 2 to 4, and you have the 4 proton here. For this reason, so this donation are possible. But any atoms with the adjacent to the carbocation stabilizing the carbocation like this way, this they have donated lone pair, so 2 2. So this can also possible when that of the chloride that can also donate its electrons and that can stabilize your carbocation. So the importance of pi donations depends on the how loosely the atom holds on the lone pair. Like nitrogen, which have the less electronegative as compared to oxygen and fluorine, so nitrogen will be best donor. So for these cases, this will be more stable carbocation as compared to when there will be oxygen or fluorine. Nitrogen that due to less electronegative, so this lone pair loosely bound to this nitrogen, this can easily donate to the carbocation. But also when you are increasing the size, so that pi donation become less important because the 2p orbital when the larger size, so that cannot be better overlap. So fluorine will be your best donor as compared to the chlorine bromine iodide, as bromine iodide have that less crow less electronegative, but due to that orbital overlap they are not matching, so fluorine will be best donor. Then the next, sorry, next, but the when there will be destabilizing, but when we have that we have the carbocation, but we have that negative charge adjacent to the carbocation, so this will be del fluorine will be more electronegative, which become this carbon as del plus, and you have the del plus adjacent to the carbocation, so this become less stable due to the highly electronegative fluorine atom. Also this nitrogen have that no lone pair, and also this have the electronegative, so this will be del minus. These two positive charge are intact, so this will be not stabilize your carbocation. More example, destabilizing group like NO2, SO2, or oxygen, or CN adjacent to the carbocation, that will be destabilize your carbocation. Remember that the lone pair has to be atom attached to the carbocation in order to stabilize its lone pair to form two atoms way don't count. Like this lone pair is not stabilizing because the nitrogen has the less than a full octet and insignificant resonance form, like these cases. Next is that from that s electron point of view, how that stabilize when you have that sp carbocation which have the positive charge, which is the less stable, because that as you consider a cell, so this is your nucleus, this is your s orbital, this is your nucleus with the positive charge. So s orbital is adjacent to the positive charge. So when we have the more s character like sp orbital, so we have the 50% s character. sp2, like we have that 33% s character, and sp3 we have the 25% s character. So sp3 cases have that s character is less, and when your carbocations nearing to that sp3 carbon atom, so that will be stabilize your carbocation more. Like your sp carbocation, the more s character, the less stable, but for the anion cases, so the more s character, that means that more s character, that means more positive charge, so more positive charge can stabilize that negative, so that will be more stable anion. But carbocation cases, more s character, more positive charge, which will be destabilize your carbocation. So why not you think that increase s character increases the electronegativity of the carbocation. So increase s character, that means more negative. Increase s character, that is the more positive in this carbocation, and which will be more stable for the anion cases but less stable in the carbocation cases. So it is similar how to stability of the of an atom and empty orbital decreases with increasing the electronegativity. The boron, carbon, not all of these species have 6 valence electron. Fluorine, so most electronegative, less stable, empty orbital. and some that value which like how this carbocation will be stabilized. So the carbocation ranked by hydrated affinities in kilocalorie per mole. The measures the energy gap of gas phase reaction in the carbocations like the methyl one, which can easily from that hydrated because this is an unstable one. So most unstable. So it's 315 kilocalorie per mole. With increasing that your carbocation stability is increases. So carbocation stability is increases stability of carbocation. So that benzylic one that stability 238, but this aromatic which is the most stable carbocation which can easily stable. For this reaction, so some question about that. For that, how this the SN1 reaction? So this is the benzylic one. That the benzylic also that will be some methyl group. So this methyl group that hyperconjugation probability also this that del minus of carbons also stabilize your carbocation. That will help the stability of carbocation. Here that more CH3, more hyperconjugation. Also this one here the benzylic carbocation which will be stabilized by the resonance. So the stability. So this one here also the resonance is possible. So this one the highest stable carbocation, this is the second, and this one the third. So the reactivity of this one is the most reactive, one, two, three. So one will be most reactive, then second, then third. So like that type of question comes like this question. So when you have what will be the product of this reaction? So like this one can go by. So first you think this one SN1 or SN2 reaction. So that OH minus and water. So I minus your leaving group and the OH minus will be attack here and your leaving group comes out. So this one like a SN2 reaction. So when you have that this because this carbocation are not that much stabilized, which can favor that SN1 reaction that much. And if you give that all the possible products, so then you can give that SN1 product also and SN2 product also. These carbocation are not that much stable, so that SN1 not that much favorable. So we are only giving the SN2 product. So what will be the SN2 product? Like this. So in the next classes, we also talking about how the SN2 reaction going on and what are the conditions needed to for that SN2 reaction. So this will be your OH minus, which is the below the plane because this hydrate is above the plane, and this will be your which is also below the plane. This will be your SN1 product. This, when we are giving heat in this reaction, this can give E2 product also. This reaction also we are how the E2 reaction is going on. We are going to give in next classes. So E2 will be like that. So that will be elimination. So how the elimination will happen? The leaving group which have that hydrogen here, right? That E2 reaction we have to remember that the hydrogen should be uh, if your leaving group is the above the plane, so hydrogen should be below the plane. So the two hydrogen possible. So which hydrogen have the above the plane? So that OH minus can take this hydrogen and remove your leaving group. So you are getting this product. The hydrogen is the above the plane. So from this side, it's not getting. But when we have like this type, both the leaving group, this iodide and methyl, which both are above the plane. So there will be the hydrogen, which is the below the plane, and also hydrogen the below the plane. So now that 2E2 product can be formed. Like here, we can get that one product like this. This will be a methyl, and if this will be like this, so your methyl is above the plane. It's also possible. For that SN1, so both the cases only this one, and when the methyl is up, so then the, this cases the SN1 product, SN2 product will be this will be OH minus is down. In the next reaction, what will be the probable product? For these cases, so this your iodide rich leaving group. Here, if that iodide is going on, so this will be this carbocation, which is the 2-degree carbocation, which is stable. So here, both SN1 product SN2 product, both are possible. For your water, the polar protic solvent like water, mostly favorable the SN1 reaction. Your carbocation and not stabilize here. This one also polar protic solvent, so both the SN1 reaction, SN2 also possible. The SN1 product will be like this. One cases where OM is up. So for SN1 there will be, we are getting the inversion of product. So one cases OME will be down. For SN2, if we are getting one product. This reaction also probable that E2 reaction, if they are giving the E2, so this is the iodide, hydrogen, this can give, and it will be taken out, so the E2 product will be like this. Another E2 also possible from this side. The next product will be like this. So up to today, if you have any doubts regarding today's class, then you can ask now. So we also meet in the next classes. So in next classes we are talking about the addition to reaction and elimination reaction.